Analyzing radical and rational functions, lesson 5. We're going to do graphs of rational functions. So we're kind of putting it all together in terms of asymptotes, point of discontinuity, different things like that in which we're going to focus on in order to graph them. So review, okay, so we know we have the function of rational functions of, rational form of two functions, which is fraction form. Okay, so you have asymptotes when they have no factors in common. So when there's no factors in common, nothing you cancel, then you straight up have asymptotes. You know there's nothing that you can do in terms of the graph is going to break there. Okay, we did also know our horizontal asymptotes happen kind of three ways. The top's growing faster, there is none. The bottom's growing faster, it's 0. If they're growing equally, it's the coefficient of their the ratio of their coefficients. Okay, so that's what all this is saying here in summary for horizontal. Your points of discontinuity is your points which have a hole, and that's when you cancel a factor. So you recognize that with an open circle at that x location that you canceled. Okay, all the stuff we talked about yesterday. To find the exact point, what do we do to find the exact point from yesterday? Yeah, the simplified version, you plug in what you canceled. So if you cancel an x minus 3, you plug in 3 to the what's left of the canceled version. Okay, the simplified version, okay? Good. So that's a summary of that whole first page there. So we can just kind of get right to it. All right, so then investigating the graphs of the rational functions with no discontinuity. So look at this one. They're telling us it has no discontinuity. So let's just answer the question. Does a function have any non-permissible values? They kind of gave it away. If there's no discontinuities, there's no non-permissibles, right? Every non-permissible value is a point of discontinuity. We talked about that. This one doesn't have one because everything you plug in will be positive. So no matter what, the bottom's going to be positive. It never will be -1. It will never cancel. So this one is no. Okay. State the domain of the function, xer. There's no problems for x. Okay. The max value of the function will occur when the denominator is at its lowest value. Determine the maximum value of the function. So that's going to be simply what they're saying is that if you look at it, just think about it this way. If I plug in a 1, right? 1 squared is 1, 1 plus 2 is 1/2. And then every number I plug in after that, it's getting smaller because it goes 1/2. And then if I put in 3, 1/10. If I put in 4, 1/17. You see it keeps getting smaller. So then the biggest value is going to be when I plug in 0. If I plug in 0, it's 1/1. That's going to be the highest point of this graph. Okay, so the maximum value is going to be 0, 1 for the max. So let me explain that again, because if you keep plugging in values for x, 1, 2, 3, 4, it keeps getting smaller, smaller, closer and closer to 0. Why does it keep getting closer to 0? Well, is the bottom growing faster than the top? And what's that mean? Horizontal asymptote at 0. Since the bottom's growing faster than the top, we know it's horizontal asymptote at 0, so it's kind of coming together. Okay, explain why the value f of x can never be negative, because anything squared is positive. Okay, does a function have any zeros? It does not. Okay, there's no zeros, so it doesn't have any x-intercepts, which makes sense because it's approaching 0 on both sides but never touching it. So it's actually a little mini hill. Okay, and we'll look at that in a second. Okay, and then it says use the answers above to suggest a possible range. So what's the range? The range is going to be, so I'm just going to answer it up here. Okay, so this is part F. Okay, so what do you think the range is? Yep, greater than 0 is part of it. But it has a max, right? What's the max? 1. So it's greater than 0, less than or equal to 1. Okay, it's between 0 and 1. But it can be 1, it can't be 0. Okay? Good. All right, and this says use a graph calculator to plug it in. You can use your graph calculator. I'm just going to draw it for you, but you can go ahead and plug it in if you want to look at it. So what it looks like is, so here's 1. It simply looks like this. Like that. Like that. That's what the graph is going to look like. So I'm going to stay on this page here. So keep going down your workbook if you want. We have one more piece, just H. So this was G. Make sure you put the brackets right over x squared plus 1. So if you put this in your calculator, make sure you put it like this, 1 over x squared plus 1 brackets. Because those of you guys that just put it like this, that's 1 over x squared plus 1. Then it does plus 1 separate. That's why a lot of you guys had issues. Got to put brackets on the bottom there because of order operations. Okay? All right, last piece here, H. Vertical asymptote, none. So part A, there's none. Is there a point of discontinuity? No. And is there a horizontal asymptote? Yes. Y equals 0. Because the bottom's growing faster than the top. Okay, and that's all for that graph there. Okay. All right. Now we're going to look at a couple of these graphs here. Any questions that? Sorry, any questions? It's going to go quick today. Okay. All right. So then for these ones, we're going to look at all these different graphs here. So we just did I, right? That's the same one we just did. Okay. So it's already on here. So it says graph calculator screenshots of rational functions that are showing using the window. And so then we're going to use these pictures to kind of answer the questions below. So I'm going to go below here, but you're going to refer to these pictures. Okay. So let's look. State the horizontal asymptote of each graph. So for all those graphs, state the horizontal asymptote. So let's do this together. What is the first one? We already did this one. Yep, y equals 0. Second one. Yep, it's growing faster on the bottom still, right? Y equals 0. Third one. Y equals 1. X squared, coefficients are 1 over 1. Okay, and the fourth one, none. Okay, we see that illustration there of our horizontal asymptotes. So the first two, the bottom is growing faster. The third one is equal, so it's the coefficients. The fourth one, the top is growing faster, so none. Okay. Do the equations above agree with these rules? Yes. Okay, so in the review to begin the lesson. So it says yes. Look at part 2 with a little bit of shade. But part 2, the important part is, again, like I told you guys yesterday, we're that one that crossed for the warm-up. Asymptote is still something it's approaching. So even though it twists through for I, part 2, let me go up and explain this here. This is how I kind of think of it. It's kind of, so yes, this is an asymptote. And you may be saying, well, it's crossing there. You're right. But the reason it's doing that is because of these guys' relationship is an odd relationship, and so it can twist through. And what's happening is that that's the only spot it's going through, but it's still forming to that asymptote. So that asymptote is still being approached. That's the important part. Don't think of asymptote as never crossing. Think about approaching. Okay? And so that's what's happening there that you may be confused with. All right? So anyways, the equations agree with the rules. They just say yes for this. And I explained that to kind of give you a full yes, because I'm sure you're thinking, well, part 2, no. Okay, so then it says, explain why x infinity, the graph of x over x squared plus 1, approaches the asymptote of y equals 0 from above, but as x goes to negative infinity, approaches from below. So why is that happening? So this is explaining what we're talking about. Well, as x is growing to infinity, so to the right, the numerator and the denominator are positive. So then what they're saying is, as it's going to infinity, that's positive, that's positive. So positive keeps you above. Okay, so that's why it's above. And then as x approaches negative infinity, the numerator, I'm going to, oh, dang it. Sorry, let's get that fixed first here. Okay, so numerator. Okay, for as it goes to, so it's infinity, so negative infinity. The numerator, so let's abbreviate this time. Numerator this time is negative, and the denominator is positive. So negative or positive gives you a negative. So that's why it twists. Okay. Explain why the graph of h of x has no points in quadrants 3 and 4. So why does it have no points in 3 and 4? So why does it never go below? Because below is what? Everything squared is always going to be? Everything squared is always going to be? So the whole thing's never going to be in the negative section. So there's no chance for negative values. Okay? All right. And then we just got 2 examples and call it a day. Okay, questions? Doing all right? Okay. So, consider the following functions. Okay, those are the following functions. And what's it want us to do with them here? Okay, without sketching the graph of the function, determine which functions have no discontinuities, no vertical asymptotes, no horizontal asymptotes, okay, all these things. So what we have to do is we need to simplify these and figure out what's going on within these pictures, all right? So this one right here, is that simplified? Yeah, it's simplified, so we're good to go there. Can I factor the bottom here? Trick. Nope. That's not a difference of squares, but the top is, right? So the top's going to be, it doesn't matter about the top except for the zeros. It tells you your x-intercepts, right? Because whatever makes your 0. So yeah, all right? So we're just kind of breaking these down so we can see what's going on. Now the second or the third one, C, we can factor the bottom. Now that is a difference of squares. So we see here, we get the x plus 4, x minus 4. Same thing on the D. Oh, wait. That's no, that's right. Okay. No, that's not right. That's not 4s. Those are 2s, yeah? These are 2s. The next one I was on 2 and 2. And then this one is x plus 2. That's the one that we can do. This point of discontinuity. The one on the right there, that's as far as that goes. That doesn't simplify at all. Okay. This one simplifies a little bit. Okay. So with this one, I think all I'd do here is I just would pull a negative out, I think, just to see if anything changes. But nothing factors from there, and the negatives cancel, so that's pretty much all you can do there. I'd pull a negative out in this one too. And then that factors. I'm just going to factor it here, but I won't rewrite the top. Okay. And then the last couple here, x plus 2, x minus 2 over x plus 2. Oh, pull out an x. If we pull out an x, that's x squared minus 4, which then we can go again. Pull out an x. There we go. Okay, so I'll pause the video. I'll let you get those down. Those are all the ones that we want to see what they are simplified so we can answer the questions for A through F there. Okay, so I'll pause. Okay, so let's go ahead and move on here just to this section now. Let's answer the questions. So which of those, all those graphs up there, have no discontinuities? So no discontinuities is there's no way to get 0 on the bottom. So which ones can we not get 0 on the bottom? Number 1 we can. B, we can't, because number 1 is just -4, right? Discontinuity is not about canceling. Discontinuity is that you can't get 0 on the bottom. B, we can't get 0 on the bottom. And G, yep, G we can't as either. Okay, that's the only 2. Because x squared plus 4 can never be 0. No matter what I put in, I can't get a -4 by squaring something. Okay? Okay, no vertical asymptotes. So which ones do not have any vertical asymptotes? So these, remember, points of discontinuity are okay. So obviously we're going to steal the ones we just did, right? If there's no discontinuities, they don't have asymptotes. So that's going to be here too. And then is there one with, oh, excuse me. No, that's right. Yeah, points of discontinuity. So is there any that don't, like, that cancel? And that's all that happens. Like where it cancels, and then what's left is going to be the line. G, or wait, what'd you say? D. But D, we still have a vertical asymptote from the x minus 2. So he's right. The x plus 2's cancel, but you're left with a vertical asymptote from the x minus 2 being on bottom. Okay, that's good. I is correct. So look at I. Now, I think, again, D is really good guess. Look at D and I, the difference. The x minus 2 is on top for I, but it's on bottom for D. The bottom's a problem. That's a vertical asymptote. Okay, we good? Okay, cool. No horizontal asymptotes. So we're looking, if there's no horizontal asymptotes, we're looking for what? The top to be growing faster. So all the spots where the top's growing faster. E, I, and J. Good. Good. Okay. The x-axis as a horizontal asymptote. So simply they're saying your horizontal asymptote is what? 0, right? So which one is your horizontal asymptote? 0. So that's where the bottom's growing faster. C. Isn't D one? Yep. So D. Okay, and then her G. Okay, correct. That's all three. Good work. And then a horizontal asymptote with the equation y equals 1. So for it to move off of there, they have to be growing the same. So which ones grow the same? So wait, what's one at a time? Just B, okay. F, yeah. Yeah. You're missing one. A, the first one, yeah. A, B, F, H. Good. And which ones have the points of discontinuity? They'll be open circle because you cancel a factor. So which ones cancel a factor? D. D, I, good. There's one more. J, good. Yep, so that one has 2 points of discontinuity, yep. On J, it has x and the x minus 4. Or wait. Oh, no, just the x cancels. Sorry, just the x on J. That is the point discontinuity. So at 0 is the point discontinuity, Aiden. Okay, last example here. Any questions on any of those? That's good right there. Good summary of everything we want to know for those. All right. Algebraically determine the equations of the asymptotes and coordinates of any points of discontinuity on the graph of this function. State the domain and range of the function. So factor the bottom is the first thing we want to do. So the top, we got 2x minus 1. Top, x minus 5. The bottom, what's it factor to? Yep, x minus 5, x plus 3. All right, so algebraic determining equation of the asymptotes. So first off, what is the equation of, let's do my horizontal first. What's my horizontal asymptote here? Nope. Nope. The top's going to be a 2x squared. The bottom is an x squared. So 2. You guys see that? See right here? 2x times x. So when I FOIL this guy out, it's going to be 2x squared. Down here is a single x squared. So 2x squared over 1x squared, 2 to 1, 2. Okay? Vertical asymptote. So what's the vertical asymptote? There's only one. -3. Because this one doesn't cancel. Okay, and your point of discontinuity, let's just call it PD, I guess. Point of discontinuity is going to be at 5. And what's that point going to be? How do we find that? We have to plug it in after we cancel, right? So cancel, and then you plug 5 in to what's left. 9 over 8. Yep, 5 and 9 over 8. Good, Aiden. Okay. Now, last thing I do is the domain and range. Okay, so what's the domain? What's the domain? Yep, can't be -3 and 5, positive 5, because it's -5. Yep, just x can't be -3 or 5. And then for all reals, yep. Okay, and then how about your range? Can't be 2. What's that? Nope. One more piece. Can't be 9/8, right? 9/8 is an open hole, so it can't be that value either. Okay, that's good. All right, good job, good job. Cool.